All right. Hey, everybody. So today we are doing topic 37, which is the first of two time series topics. Pretty much how they're split up is the first one, we're going to talk about time series data and how to kind of do EDA for time series. And then tomorrow we'll go more in depth into the modeling. So today we're going to set up a lot of the things for time series modeling. And then tomorrow we're going to talk about the models themselves. They're actually very, very similar to linear models. So for example, you'll see some things that look fairly similar. Well, tomorrow you'll see things that look fairly similar to stats models OS, because stats models is the library that we're going to be using primarily for time series. To preface, the time series project that is for phase 4, the provided data set is a bunch of housing data for a bunch of different zip codes. I think there's maybe like over 100 different zip codes that you're given. And the idea of the project is to implement time series modeling on as many of the zip codes as you can, and then make recommendations on which zip code is a good investment from the end of that training period. More details about that when we, of course, kick off the project at the end of next week. For more context, this kind of time series is very traditional time series. So it is very linear models. It is not getting into neural networks yet. Of course, there are some neural network information that I will talk about next week that you can apply time series with. But I will say that these time series models that we're going to be working with at the end of today, we'll start talking about it a little bit, but mostly for tomorrow, they're still very primarily used in traditional industries. So finance and real estate being the most prevalent ones. Other industries that do time series forecasting typically tend to use something a little bit more advanced, or they rework their data to use regular classification or regression models for. So with that information, you can decide whether you're going to work on this or not. But cool. Let's get started. So to just set the stage, what exactly is time series data? Time series data is, and let me just zoom in a little bit more, basically a series of values of a quantity obtained at successive times, often with equal intervals between them. So often with equal intervals, but not always the case. Actually, stock data is one example where you don't actually have stock data for any days where the stock market is not open. So like weekends, public holidays, things like that. So you end up having gaps in your data, which is not a big deal, honestly. You'll see in a little bit, or we'll see tomorrow when we get to the models. As an example, daily temperatures within July. So you'll get what, 31? Yeah, you'll get 31 days of data, so on and so forth. There's also the weekly average price of a stock in the past year. So you get 52 data points, all evenly spaced out. And then also the average annual government budget in the past 30 years. So that'll be 30 data points of the average annual government budget. So right now we're going to focus on univariate time series that talks about just a single observation of variable at different but equal time intervals. Cool. Any like beginning questions on this stuff? Okay, so I do want to draw the line between regression and forecasting because it can look very, very similar. So the data for regression and time series forecasting looks pretty much exactly the same. You are predicting a continuous variable. Now, for forecasting today, what we're going to talk about in the bulk of tomorrow, we're just going to have one variable. So for example, you have the price of like the S&P 500, and you're going to use that to predict itself. So it's just doing a forecast on itself. So you can sort of think about that as like if you had your regression, just your Y column. However, I will briefly talk about a scenario where you can bring in other variables like exogenous variables. So let's say you want to predict S&P 500 stock, you can use other things like maybe, I don't know, interest rates. You can bring in, what are some other things? Interest rates, price of some other stocks, for example. You can actually use those as features to help you make better forecasts. Because if you think about it, if you're just using the stock price itself to predict itself, might not be all the information that you need, but just heads up. So therefore, the data can look very, very similar. But what is the difference between a regression task and a forecasting task? So one, it depends on your business case because they can yield very different results. but I like to think of forecasting as specifically predicting into the future, and that your train test split, and we'll actually talk about train test split more tomorrow for time series, your train test split is usually done in a chronological way. So let's say I'm trying to predict, I don't know, S&P 500 again. We're gonna try and predict S&P 500 using the past 20 years of data. Maybe our split will be, I'll use 19 years as my train set, my last 1 year as my test set to see how it's predicting. And then we can forecast further into the future. That is quite different from our train test split that we were dealing with up until this point, where our train test split was completely randomized, because the order of the data points in regression doesn't matter. Same with classification. The order of your data points does not matter. However, in time series, it does matter. It just has to be in chronological order. A lot of time series tasks can actually be reworked and done in regression or classification. You just don't have that element of, okay, this point came after this point came after this point. So if for some reason your time series models aren't doing very well, you can definitely pivot to doing more of a regression or classification task. But yeah, it really depends on your business case, especially. Okay. So now that we know a little bit about time series data, what are some main characteristics to take note of, especially as you're prepping your data for time series modeling? So the most notable characteristics in time series data are the patterns that could emerge. They're specifically trends and seasonality. So trend is just kind of like an overall movement of your data. So for example, with this S&P 500 ETF, I don't know when this was taken, but you would say, and this I think is like common jargon, you would say, okay, this is overall increasing. It has an overall increasing trend. And that's what you would say in a data science context as well. Trend is one thing. And then also there's seasonality, patterns that occur as a function of specific seasons. So perhaps if you're looking at housing prices, I mean, I don't know much about housing prices in the real world, but perhaps there's a yearly trend, like there's always super expensive in the summer and much cheaper in the winter relatively. And then you have this like overall like up and down trend that reoccurs yearly. And maybe they can both occur together. Trend and seasonality can occur together. I mean, I'm sure you've seen, like, if you've ever seen things about like the business cycle and stuff like that, you might have seen like kind of repeating motifs of like up and down, but also generally going up. So trend and seasonality can be combined. When you're looking at trend and seasonality, I'll talk about stationarity in a little bit, but with seasonality, and there are also ways to do that in data science, which we'll talk about that more tomorrow. For trend and seasonality, as you're doing your very initial EDA, it's important that you note these down. If you're doing a forecast of S&P 500, this ETF, for example, maybe I would even make some notes saying, okay, there is a slight upward trend. Maybe it starts off fairly even from whatever this date to whatever this date is. And then there's a more prominent upward trend this date onwards. If there was seasonality, you can even say, okay, it looks like there is a yearly trend, or it looks like there's a, sorry, not yearly trend. It looks like the seasonality is perhaps yearly, or depending on how granular your data is, maybe you can go and explore, all right, like within the days of the week, is there seasonality there? Because those are things that you can incorporate into your model as well. Okay, so an important pattern in time series that occurs is stationarity, which is actually one of the assumptions for time series forecasting and modeling. One of the assumptions is that your data can be stationarized. And stationarity just means the absence of a trend, which we'll talk about in a little bit. But any questions about overall trend and seasonality? Cool, okay. So to talk about stationarity is basically what you want to achieve. And that is as a result of removing trends. So yeah, again, stationarity is an assumption that lays the foundation for time series modeling. So if your data cannot achieve stationarity, you will not have consistent or reliable time series models. So what is stationary data? It is basically data in which the summary statistics, mean, variance, and covariance are not a function of time. So not a function of time, what does that mean? So for the mean, you want it to be pretty constant. You don't want to see any upward trend. And we'll talk about how to remove this upward trend in a little bit as well. So this is a stationary series because the mean across different time periods is roughly the same. Non-stationary series, you can see that if I were to divide this into chunks, they're going to end up with different means, or there is still like an upward increase in the mean at different time periods, and that's what we don't want. There's also constant variance, homoscedasticity, which is what we want. We don't want periods of more volatility versus other periods. And that's something that we can take care of as well. And same with covariance. The covariance is basically talking about the evenness of seasons. So for example, you can see here, let's just say that each of these things is 1 year in the stationary series. In this non-stationary series, it looks like the seasonality changes midway through the time series. So like over here, maybe it's the yearly seasonality, but here we go into, for example, maybe monthly or quarterly seasonality. So why does data need to be stationary for modeling? I think this will make a little bit more sense when we get into the actual models tomorrow. But stationary is important because it will model, without it, a model describing the data will vary in accuracy at different time points. So basically the consistency. And we'll sort of see why that is when we talk about the models tomorrow. You can start thinking of it as, we're actually going to use linear features, but the features will be the time series itself. That doesn't make sense. We'll get to it tomorrow. But also stationarity lays the foundations of typical time series models, such as AR models, MA models, and ARMA models. We're actually going to talk about these three and more tomorrow. A violation of stationarity can cause problems in prediction. So how do we test for stationarity? First, we look at the visualization. And I saw a typo that I'm going to fix right now. Okay, there we go. All right, so several ways you can test for stationarity. You don't have to have perfectly stationary data. That's one thing that's important to mention. It is preferable that your data is stationary, for example, like, looking like this, but in the real world, pretty much no data will look like this. Same as when we were dealing with linear regression. You never have data that perfectly fits your QQ plot, that perfectly has, homoscedasticity across. So you just need to have enough stationarity for consistency. So one way to do it is by examining the visualization. So just plot your data. So this is the example data that we're going to use. It's the sales of shampoo over a 3-year period. And it looks like this. So as you can see from here, not stationary. The fact that it already trends upwards over these 36 data points is already a sign that this is not stationary. So cool, we don't have stationarity here. Another way we can do this is by examining the summary statistics. So what we're doing here is we're just splitting our data set into 2 parts. So for example, we just split it right in the middle. So you can see that we're just splitting this 36-point data set down the middle, and look at the means and variances of both sides. So here you can see that the means are already very different. Well, quite obviously, because this trends upwards, the mean of this is going to be much higher than this. So the mean here is 203 for the first half, 421 for the second half. So the mean pretty much doubles across the 2 different time blocks. And same with variance. Variance, even though it's a squared value, you can see that the variance is also quite different. 3,300, close to 3,400 for the first half, and then 17,000 in the second half, because the second half, you can see, because it spans more values, the variance is much larger. These 2 methods of just, examining the visualization, doing these summary statistics, very, very simple ways of determining whether that's stationarity. If you have a very small data set, this is an easy thing to do. However, what is the data science way of doing this? We use something called the Dickey-Fuller test. So this Dickey-Fuller test comes from stats models, and it's a statistical test for testing stationarity. So the null hypothesis is that it is not stationary. So if the test statistic is less than critical value, we want to reject the null hypothesis and say that the series is stationary. So basically what we want, low p-value. So I've linked the documentation for the Dickey-Fuller test over here. AD-Fuller just stands for augmented Dickey-Fuller. And it comes out as stats models over here. So all you have to do is just take your data and run it through AD Fuller. So you can see here, I have my results here, and I'm actually turning my results into a data frame. So if I rerun this, oh, did I run this yet? Okay, let me rerun all of these real quick. Go. Okay. So these are our results. Actually, this is the raw form of the results that I'm actually just coercing into a data frame so it's easier to see. This is the Dickey-Fuller test results. Basically what we have here, this is our test statistic, but it automatically just gives us our p-value as well, so we don't have to compare our test statistic. It's using 10 lags, and what this is, we'll talk about it later, and it's doing this on 25 observations. Basically what's happening here, if you look at the full output of the Dickey-Fuller test, it also gives you these t-statistics at various confidence intervals. And the fact that this is larger is going to automatically reject the null hypothesis, is not going to reject the null hypothesis. So by this p-value of 1, which means that it is definitely not stationary, you can conclude that it's not stationary, basically. Any questions about this test? It's a very, very typical stationary test that you should do in your data prior to any time series modeling, or you can even use it for EDA to see if your target variable or any of the features are stationary or not. Okay, so there's a couple of different things that you can do if you don't have stationary data. The most common one is differencing, which we're going to talk about later, but you can also do other things. You can also do a log transform to, flatten out your data or make the trend a little bit more consistent. You can even square your data, any transformation that you want that you think will help. You can kind of, if you're familiar with like functions and math functionality, you can sort of look at this and be like, all right, what can I do to transform this into something that might be easier to stationarize? And this really does come with practice and a bunch of trial and error, honestly. Okay, but the main thing that we can do is differencing. Okay, so some terminology before we get into differencing. We're gonna hear the word lag a lot when we talk about time series. So for some specific point t, the observed xt minus 1 is called the ith lag of t. So basically, if there's one lag, you're looking at yesterday's information or the day before. If there's 2 lags, it will look 2 back. So differencing makes use of the lag, because what differencing does is it actually looks at the change in your values over time. So we use differencing to remove the data's dependence on time. It removes temporal dependence. And it's basically performed by subtracting the previous observation, if it's lag equal to 1, from the current observation. So the difference is observation t minus observation t minus 1. So if we have a time series data set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we want to difference by lag equal to 1, what is the result? So you're basically taking each data point, subtracting the point before it, and because this is 1 through 10, all of the integers, it's going to have consistent values. So from a series that would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you end up with all ones. So here's a manual function that's just doing the differencing. You can see that I'm just appending the difference value, and I'm just taking dataset I minus dataset I minus interval, returning that. So if I'm taking the difference of 1 through 10, it's going to be all ones. One thing to also note is that whenever you do a difference, you actually lose one data point, or you lose however many lags number of data points when you're doing your differencing, because if you're doing the very, very first data point, you cannot find the difference of the first data point, if that makes sense. We'll see an example of that later by using the NumPy function. But differencing is sort of, it's just literally taking the difference between data points. And you can do this at different intervals as well. So if I were to do interval equal to 2, you actually end up with a bunch of 2s and 2 fewer data points than what we started with. Questions about differencing? Okay. So let's take a look at what differencing looks like with pandas. So pandas actually has a built-in differencing function, very, very useful, especially if you want to look at changes. So here what I'm doing is pretty much just shampoo.diff what I'm doing here is just changing the name of the column. So not a big deal here. So I'm just doing the difference of the shampoo prices. So from here, you can see that the first one becomes a null value because we cannot find the difference of the very first value if we're using one lag. So with that, if we replot the difference data, you can see that we don't have that upward trend anymore because we're just looking at the daily or monthly changes in average shampoo prices. So because of that, we've removed that upward trend. This now is just the changes in prices over time. Questions about this transformation that we've done? Okay, now let's just take this data, run it through Dickey-Fuller, see if it's stationary enough now. So here I'm just taking the difference shampoo data, and you'll see I have one here because the first data point is a null value and it throws an error if you have any null values. So I'm doing one over there. When I rerun, you can see that my p-value is now sufficiently small, below 0.05. That's usually a good enough threshold. So yeah, just based on this, you can see that our data, just by doing one difference, is stationary enough. Cool. So sometimes we have to difference the difference data to get stationary data, especially if you have a trend that looks like it's exponentially increasing. You have to first remove that exponential part and then remove that linear upward trend. So the number of times that we have to difference our data is the order of differencing. And we'll use this information later on when building our models. So let's just say you have a data set and you do this process and it still does not pass the Dickey-Fuller test. You can difference it again. So you can do .diff again. Let me see if this will work. I think I might have to do 2 over here. Cool. .diff is also still statistically significantly stationary enough. So in other data sets, you might see that this has a better impact on your data for achieving stationarity. So let me just change this back. Sweet. Okay. All right, so yeah, the number of times that we have to difference our data is the order of differencing. Keep this in mind for when we talk about our models tomorrow. So
a quick question. So if we do it the first time and it says it's kind of good enough, would it make sense if our model isn't performing too well to do it again to try to get it closer and closer to a stationary? Would that affect, I guess, the performance of our models? That might be
yes.
that a little bit.
No, yes, absolutely. There are definitely going to be a range of order of differencing where it makes sense to test your model for. So very similar as to what we were doing last phase, you can actually test your model with different orders of differencing. I'm going to show you all a process tomorrow. There's also like a grid search equivalent for time series modeling where you can actually test different parameters of your data too. So
Perfect.
That's definitely something to look out for.
Thank you.
Awesome. Sweet. All right. So after differencing, the next group of things that we want to look at is autocorrelation. So next we want to address any autocorrelation that remains in a difference series. So time series exhibits 2 kinds of behaviors, and often you can predict a value in time series using a past value of values. So other times past values can be very misleading, like the stock market, which is very, very random. So you actually don't want to use past data. But in some cases, it might be useful to use past data, right? You can probably imagine if you have something that is consistently increasing in value over time, you want to take into account yesterday's price to make forecasts for today's price and tomorrow's price and so on and so forth. So in order to take note of that, we make use of autocorrelation, and how we use autocorrelation in our models. We'll talk about that tomorrow. Actually, it'll sort of make sense, I think, after we talk about what autocorrelation is. So, okay, this is just additional reading. So autocorrelation, and we know regular correlation, right? When 2 things are correlated with each other, they just move together, right? If something that we saw is like, let's say what, price and square foot were fairly correlated with each other because as square footage goes up, price goes up, right? So autocorrelation is when a time series is correlated with itself. So let's take a look at some lags. So first I'm looking at shampoo sales lag 1, and you can see here when I concatenate these 2 together, this lag 1, I didn't change this this column title, but this is basically the same time series shifted by 1. So you have a NaN value up here. This, I just cut off the last value. Now, if I plot these values, you can see that they are they kind of move together. And that's also the case when I look at 2 legs, kind of. You can also technically plot this in a scatter plot. So if I do plt.scatter and we look at shampoo versus shampoo sales lag 1, cool. You can see that there's kind of a positive correlation there. And that correlation can be very, very useful because that means that tomorrow's price is kind of correlated to today's price with some coefficient. So you can sort of see where this comes in, with where this kind of calls back some of the stuff that we learned about in linear regression. If these things are correlated, that means with some coefficient, we can predict tomorrow's price using today's price. Same thing, we can do the same thing for shampoo sales like 2 as well. I don't know if this is better or worse, we'll find out. But yeah, that's what autocorrelation is. So to look at autocorrelation, and autocorrelation can vary when you're looking at different lag times, right? Like here I'm only looking at lag 1, lag 2. What if there is some sort of perhaps seasonality, and if it's weekly seasonality, there's a very, very high correlation between day 1 and plus 7 days, so day 8. So that's also something that you can look out for. But any questions about the concept of autocorrelation? Basically, it's a time series correlated with itself, shifted some number of time periods. Questions about that?
Yeah, quick question. So looking at lag 2 versus lag 1, at the very end, lag 1 looks like it's trending up with the original lag, and this one is trending down. Is that like a sign that lag 1 would be better used?
Not necessarily, because you're kind of looking at correlation as a whole, because maybe there's this one last point that doesn't really gel, but it is possible that, you know, shifted 2 lags, more other points are correlated, add to the correlation, if that makes sense.
Yes, gotcha.
Okay, yeah, because correlation at the end of the day is still some sort of aggregation of your values. But yeah, that's a good observation. Yeah, basically you'll see this is lag 2 and this is lag 1, because correlation is kind of more better captured in a scatter plot. You can sort of see that it actually might look like that lag 2 has a stronger correlation. I don't know. We'll find out in the next couple of cells. Cool. So one built-in method that is very helpful for us to figure out autocorrelation is also in stats models is the ACF and PACF functions. So what this plot shows, and you can import it like this, and you plot autocorrelation like this. This basically will show you with however many time lags, what is the correlation coefficient. So this autocorrelation plot is just saying that at time lag 1, there's roughly like, what is this, like a 0.67 correlation. And at time lag 2, there's a 0.75 correlation. So we can actually take a look at that to confirm. Let's see, how do I do that? Oh, here, there we go. .4. Neat. Okay, so it looks like there's like a 0.72 correlation between the first and the second one. Let me see if I can add, hope this doesn't break, lag 2. Sweet, okay, cool. So we're looking at the original time series. This is the correlation with 1 lag, 0.719. With 2 lags, it is 0.85. So that actually roughly matches the graph that we were looking at, of the ACF graph, where this is about 0.72, this goes up to 0.85. The numbers don't actually gel, I think, because I'm cutting it off at some point. But yeah, kind of matches the pattern. It goes down first and then up. This graph can look very, very different depending on what your data looks like, honestly. If you have very, very seasonal data, it can actually go up and down. So for example, if there was weekly seasonality, for example, every 7th point would be very, very correlated. So that's something that's worth noting as you're doing your time series EDA as well. So yeah, looks like the first few lags. And oh, by the way, this blue shaded area is the confidence interval. So any data point that is outside of that confidence interval is a significant lag point. So yeah, it looks like the first 2 lags have some pretty strong autocorrelation. Take note of that for future model building. Usually at this stage, if you haven't built your model yet, you can say, okay, based on my ACF plot, it looks like I should take note of the first 2 lags. It's quite often, it says sometimes here, autocorrelation propagates down to the other lags. So as you can see here, if you have like a data set that looks like this, it looks like, yes, you're going to get at some point, well, 2 was more correlated than 1, right? But as you slowly shift the lag further and further away, it makes sense that your correlation might slowly go down. So a very, very common pattern to see is actually something like this, where your autocorrelation, yes, it might go up and down like a tiny bit, but overall starts going, overall has a gradual downward trend with the more number of lags that you add. So this kind of pattern autocorrelation, very, very common. So the influence of a strong autocorrelation does cause additional lags to be highly autocorrelated. So to discover the true relationship between lags, we can use PACF. Now, this link from ACF to PACF can be kind of abstract, but the way I like to think of it is, okay, let's just say that in this example, lag 1 has a correlation of, let's just say about 0.7, and this is about 0.8. Let's just use those numbers as an example. How much of this 0.8 autocorrelation is due to the fact that this 0.7 correlation exists at lag 1? Does that make sense? Anyone want to clarify anything about that? So basically, the argument is that some of this like remaining autocorrelation that happens at like lags 3, 4, 5, all the way till like 10, it slowly gradually decreases because it is still taking into account the existing autocorrelation from prior lags. And to not think about that, or to completely remove the prior lags autocorrelation impact, we can look at PACF, which is another curve. And I will say that ACF and PACF always come together. So PACF is partial autocorrelation function, where they're trying to remove the influence of intermediate lags when you're creating your plot. So this is what PACF plot looks like. And you can already see that it looks quite different. So again, it looks at correlation between a point and a particular lag without the influence of intermediary lags. So this helps us to see the direct relationship between certain lags. So from this graph, you can see, all right, there's 2 significant lags, and then it really, really drops off. So here the numbers have gone down a little bit. So this is down. Actually, this first one should be the same, but the second one has gone down. It's not higher than the first lag. And at the third lag, you can see it shoots straight down to not being significant at all. So that means even though this third one up here was like right under the threshold of being significant, you can say that a lot of the autocorrelation in the third lag was primarily due to the autocorrelation in the first 2 lags. Therefore, it drops off when you look at partial autocorrelation. Questions about that? Okay.
When would it be appropriate to use each? Like it just seems like partial autocorrelation should just be the one we would go with.
Yeah, that's fair. You actually need to use both for different kinds of modeling. And I'll get more into that. I will get more into that tomorrow when we talk about specific models. Yeah. Any other questions about ACF and PACF? All right, yeah, there are specific scenarios where, or you kind of have to evaluate both ACF and PACF together. Here I have like a kind of a summary of what we've noticed. And then this will actually go into determining how you want to start building your time series models. Because if your PACF looks like this and your ACF looks like this, you want a certain kind of model. There are some cases where the pattern can actually flip. You can actually sometimes have ACF graphs that dip down like immediately after just a couple lags, and you might see lags in PACF as well. And that's just saying that there's actually very strong partial autocorrelation or autocorrelation without caring about the intermediary lags, and actually very, very prevalent in seasonality as well. Actually most prevalent when there is seasonality, that partial autocorrelation might have more significant lag times versus regular autocorrelation. But yeah, I understand this is still a loose end, but we will definitely get to that tomorrow. But yeah, what to note for now at this point is, okay, ACF has 2 significant lags and decreases gradually. The fact that it decreases gradually, you should note down, because that is kind of important for the next step. Same for PACF, 2 significant lag and then drops off. If there's some sort of ambiguity, I highly, highly recommend that while you're doing this EDA to take note of that, because that will come into handy when you are tuning your model, which we will get to tomorrow as well. So yeah, that is all we have for time series EDA. Of course, on top of that, you want to do your regular EDA, like, plotting what the time series looks like. If you have other variables, which I'll talk about how you can use other variables tomorrow as well. If you have other variables, you will want to look at their correlation, so on and so forth. But yeah, now that we know how to analyze patterns in our time series, you can proceed with creating models to create forecasts. So I believe the notebook for tomorrow is already on the repo. If not, I will put it up there before tomorrow. But yeah, any questions on this time series EDA, or any questions at all about anything? Okay, awesome. Well, tomorrow we'll get into some time series modeling. The libraries that we're going to use, basically stats models. So look forward to that. We have our nice little output that we also had for a linear regression as well. And yeah, if you're interested in time series, let me know. By the way, just as a reminder, third blog should be getting done by the end of next week. So look at that. And then other than blogs, at the end of this week, I'm going to put out a poll on what you want to do for your phase 4 project. I understand that we wouldn't have gotten to neural networks by then, but the neural network project itself is quite straightforward. It's basically image classification. So if that's something that's immediately of interest to you, you can select that option, I guess. So there will be a poll. I will give more insight on what that's going to look like by the end of the week. Cool. All right. If there are no further questions, going once, going twice. All right, I will see you all tomorrow. We'll get into these time series models. And as usual, any questions at all, don't forget to do your blogs. Any questions at all, feel free to let me know. All right, have a good rest of your day, everybody. Bye.